All right, welcome back. Let's look at another technique for solving limits analytically. Today, that topic is called the squeeze theorem. Now, I'll be honest with you, the squeeze theorem is not something that we see a lot out in the wild, let's say, quote unquote. That is, it's not going to be one of the techniques that you use all of the time. It's important to know how to use it, and when it is necessary, it comes in very handy and it saves the day. Okay, it comes in sometimes, when there's nothing else going to work, this thing works. Okay, and in fact, what we're going to do ultimately is use the squeeze theorem to show this one very important limit is true. Now, here's what the squeeze theorem says. Suppose f, g, and h are functions such that basically g is trapped between f and h. Okay, so f of x is less than or equal to g of x is less than or equal to h of x, at least for some neighborhood, at least for some neighborhood containing c, an open interval containing c. So imagine maybe you have something like here. Let's get different colors here. Well, let's first do an axes. So something like this. So let's say you have something like this, of course. And then we have our first function. Let's say that's our let's say our g. Let's do the g first. So we have some function. That's g. Okay, so g is in red. And then we are interested in the limit as x approaches, let's say, let's call it c. And let's put c like right here. Okay, and maybe let's put like a little hole in the graph because the function does not have to be defined at c. So maybe let's put a hole right there in c. Okay, and here let's make that a little more obvious that there's a hole there. Okay, and then let's say perhaps that we then have a function f that at least when you're near c is below g. So you have some function f, doesn't really matter what it is. Oh, can't turn vertical, that's for sure. So let's fix that. So it can be above or below g, but it needs to be below g as long as we're near c. So we're below the g function as long as we are near the x value c. Okay, so there's f. And now maybe let's put g over here. Let's put g in green maybe. And again, h, we already have g. H, something like this maybe. Okay. That's a very ugly function, but you get the idea. Here's h. Now what we're saying here with the squeeze theorem is this. Now, let's say for some reason we're having trouble finding the limit of g as x approaches c. Okay? But for some reason we can quite easily find the limit as x approaches c of h and of f. So suppose we can easily find that guy, and let's just say they happen to be the same number, L. So L is a finite number. Okay? If you can show that the limit as x approaches c of f and h, that is the outside of this inequality, the outside is the limit as x approaches c of both of those, then we're guaranteed that the limit of the middle function g is also equal to L. And that's kind of what this picture is illustrating here. Let's say that the g maybe has a hole there, maybe something weird going on there, but h has no hole. Here, let me make sure that that is shown there. Like that, there is no hole in h, and there is no hole or nothing, nothing weird going on in f2. Okay, so you can easily find the limit as x approaches c of h and of f, and you get the same number, well, then that forces the limit of the red function where there's weirdness going on. It forces that function to also be that same number. Here, let's take a look. Now, you got to be careful with these. A lot of students, we go to a test and lose points on the test because they write the right answer down. They don't really justify it. You got to justify using the squeeze theorem, okay? And you got to make sure you word it correctly, because if you start, not using your limit notation correctly and just kind of writing the answer down, chances are you might be saying something that maybe seems to be superficially correct, but it's actually not mathematically correct. So let's see what we need to do. We need to say that the limit, we need to show this is true. So we need to show this is true. And if we can show that's true, and of course, this has to be true as well. So if those two things are true, then we can get the limit we're after, which is this is the result. Okay? So, example 1.4.7. If 2x is less than or equal to f of x, is less than or equal to x to the fourth minus x squared plus 2x, use the squeeze theorem to evaluate the limit is x goes to 1 of f of x. So we don't even know what f of x is. It's just some function, and we want to know the limit as x approaches 1. But we know that this is true. Okay? So maybe the first step here would be to evaluate the limit as x approaches 1 of this function and this function. Because the squeeze theorem says if you take the limit as x approaches 1 of each of those functions and you get the same value, well, then the limit of f has to be, as x approaches 1, has to be the exact same value. So let's see. So we already know like this part, okay? But let's just, for good measure, write it down again, okay? So we can say since 2x is less than or equal to f of x is less than or equal to x to the fourth minus x squared plus 2. And what else is true? Well, what do we need to show? And let's take a look at a bullet list. What is the limit as x approaches 1 of 2x? Well, notice that's a monomial. Monomials can be evaluated using direct substitution because 2x has domain all real numbers. So this equals 2 times 1, of course, equals 2. Now, what about the limit as x approaches 1? Let's get that arrow a little better. As x approaches 1 of the other function. This needs parentheses because it's a polynomial. X to the fourth minus x squared plus 2. Now, again, that's a polynomial this time, but polynomials, just like monomials, have domain all real numbers and can be evaluated using direct substitution. So this is 1 to the fourth minus 1 squared plus 2. Well, okay, 1 to the fourth is 1 minus 1. And 1 minus 1 plus 2 equals 2. So since 2x is less than or equal to f of x, is less than or equal to x to the fourth minus x squared plus 2, and the limit as x approaches 1 of 2x is 2, which equals the limit as x approaches 1 of x to the fourth minus 2x plus 2, then the squeeze theorem implies that the limit as x approaches 1 of f of x is also equal to 2. Okay? Because we've shown that the limit of the left-hand function is equal to the limit of the right-hand function, both as x approaches 1. And because of those two bullet points are true, plus the fact that f is trapped between 2x and x to the fourth minus x squared plus 2 means the squeeze theorem guarantees that the limit of the middle function f is also equal to 2. Okay? Let's look at another example. Use the squeeze theorem to evaluate the limit as x approaches 0 of x squared times sine 1 over x. Now remember, we like to use direct substitution immediately if we can, but we can't use direct substitution here because if we try to plug in a 0, 0 squared is not a problem, but we have sine of 1 over 0. We have division by 0, and that doesn't work. Okay, so we can't use direct substitution. But again, the squeeze theorem saves the day. Because what can we do here? Well, okay, so this one is a little tricky in the sense that I'm not given this. Like, I need to figure out some inequality such that x squared sine of 1 over x is between two functions. Okay, but what do I know about, sine? I know, what's the range of sine? If you think about sine, here's a very bad drawing of sine. Sine kind of looks like this. So you know this from trigonometry. What's the range of sine? Like what's the just a plain old sine function? What's that number and what's that number? Well, that number is -1, that number is +1. So it turns out if you have sine of 1 over x, the range is exactly the same. Now, why is the range the same? Because if you affect the input, so like right now we have sine of 1 over x. That 1 over x is affecting the input. It doesn't affect the range, the amplitude of the function. The way you affect the amplitude is you multiply by x squared. That affects the amplitude. You multiply on the outside of the function. So my point is that the fact that we can say since -1 is less than or equal to sine x is less than or equal to +1, that's what we know from trigonometry class. We know that -1 is less than or equal to sine of 1 over x is less than or equal to +1. Again, because the way you affect the amplitude is by multiplying on the outside of the function. And if we just change the argument to 1 over x, that's not affecting the amplitude. Okay, the overall amplitude of the function. Okay, but now that's not going to cut it for us because we need to find two functions such that the middle function is trapped between, the middle function is x squared sine 1 over x. Right now I have sine 1 over x. I need x squared sine 1 over x. So how can I do that? Well, just by simple arithmetic, or not arithmetic, algebra, we can say, so put a comma there, which implies what? Well, we can multiply every term of that inequality by x squared, right? And since x squared is non-negative, I know that doesn't reverse the signs of the inequality. We gotta be careful when we're multiplying inequalities because if you multiply by a negative sign, then you reverse the inequality. But here, x squared is always a non-negative measure. So we can multiply every area of this inequality by x squared, and we get negative x squared less than or equal to x squared times sine 1 over x is less than or equal to +1 times x squared. Okay? So since we start with just what we know from trig, and then a little more basic we know from trig, that implies that this statement is true, which is negative x squared is less than or equal to x squared times sine 1 over x, less than or equal to positive x squared. And now we have this statement. That's what we need. We've got that much. Now we just need to show that the limit of the two functions on the outside as x approaches 0 is the same number. And if we can show that, then we know that the limit of the inside function has to also be that same number. Okay? So I'm going to actually, since I'm going to replace that period with an and, okay, what's the limit? Here, I'll do a bullet list again. And the limit as x approaches 0 of the left-hand function, negative x squared. Well, that's a monomial. You can evaluate with direct substitution. That's negative 0 squared equals 0. Now, what about the right-hand function? Limit, sorry. Well, it's positive x squared. Well, okay, polynomial, use direct substitution. So the limit of the left and the right-hand function as x approaches 0 is indeed 0. Thus, the squeeze theorem, so since negative 1 is less than or equal to sine x is less than positive 1, we know that negative 1 is less than or equal to sine 1 over x, less than or equal to 1, which implies that negative x squared is less than positive x squared sine x 1 over x, less than or equal to positive x squared. And these two limits are equal to 0. The squeeze theorem implies that the limit as x approaches 0 of x squared sine 1 over x has to also be that same value, which in this case is 0. Okay, here, let's look at the graph. By the way, this is a graph that I don't even know what it looks like. And it's not like a common graph that I don't expect you to know what it looks like. Let's see what x squared sine 1 over x. Yeah, it's kind of a crazy graph. Okay, there it is. So let's zoom in. We're only concerned about the limit as you approach 0. And notice, yeah, okay, if you try to hover over 0, the function as a whole there, it's undefined. But clearly, as we approach from the left and the right of the origin, the y values are it's oscillating, but getting closer and closer and closer and closer to 0. Closer and closer and closer to 0. And we do get the limit from both sides equal to 0. So the two-sided limit is equal to 0. Okay? So there, those oscillations basically are tamed. You know, if you don't have the x squared there, the oscillations are too crazy, and we saw this in a previous video, the limit did not exist. But if you put that x squared factor out front, it tames those oscillations in some sense, and to where you actually do get a limit, which you can show according to the squeeze theorem. Okay, cool. Now, the grand finale of this video is this limit here. This is a very important limit. It's the limit as theta goes to 0 of sine theta over theta. This is going to be a limit that we need to determine, and then we're going to memorize it. We're going to add it to our limit toolbox. Why? Because it's going to turn out when trying to solve trig limits, this limit pops up a lot. And so if we have it memorized, then we don't have to reinvent the wheel every time, because to reinvent the wheel takes a little bit of work, as you're about to see. This is going to take maybe 10 or 15 minutes to do. Okay, maybe less, but we'll see. We're going to use the squeeze theorem and a little bit of trigonometry and geometry. So we want to show, you know, what this limit is equal to. Clearly, you can't use substitution, because if you try to replace the thetas with 0, you get sine theta, which is, so you get sine 0, which is 0 over 0. So you get 0 over 0 indeterminate form. So that's 0 over 0 form, which means we have to do something to figure out the value of the limit. Okay, and here is a picture that I made for us. Let's see what we can come up with. So notice in this diagram over here, this is a quarter unit circle. So the only coordinate I put on here that I labeled was 1, 0, just to show you this is the unit circle. Okay. Now notice there's like 3 objects in there. There is a kind of like a big triangle. Here, maybe I'll outline these in different colors. So there's the big triangle. Let's see if I can maybe do that in red. Big triangle. Then we have a smaller triangle. Let's do that in blue maybe. Then we have what's called a sector. A sector is kind of like a 2D ice cream cone. Oh, these colors don't show up very well. But there you go. I'll keep doing everything in different colors when I do the calculations. So we have 3 objects. And notice, okay, if you use your imagination a little bit, if we let theta vary between 0 and pi over 2, so 0 to 90 degrees, that relationship will remain constant. That is, that small triangle will always be the smallest. The sector, the cone shape, will be in the middle. And then the red right triangle will always be the biggest of the 3. Okay? So we have basically an inequality we can write. If we can write the area of each of those objects, then we can write an inequality. The area of the small triangle is less than or equal to the area of the cone, of the sector, which is less than or equal to the area of the big red right triangle. Okay? And so then we can use the squeeze theorem to find that limit eventually. Oh, sorry about that noise. Somebody, they're doing work next door, so hopefully that will not be so loud here in the very near future. Okay, yeah, turn it off. All right, so let's look at the big triangle first. Okay, the big triangle. Now let's see. Let's write the area of it. So area big red triangle. In fact, let's not do a triangle like that. Let's make it a right triangle since that is what it looks like. It's a big red right triangle. Okay? Well, what's the area of a triangle? Well, it's 1/2 base times height, right? So 1/2, what's the base of this red triangle? Well, what does the point over here say? It's the base is on the radius of that unit circle, so the base is 1. Okay? So we have 1/2 times 1 times the height. Okay, now how do you find the height? All right, well, okay, here is the height. How do you find that? Well, okay, that height is going to vary. Like if you let theta vary, well, the height's going to vary. So that means we need to find a variable expression for the height. But we can use trig. Okay, so what do we have here? We can say that what trig function relates this known base, which is 1, with the height and that theta. Well, what? Theta opposite over adjacent, right? So tan theta. So tan theta, we could say, is opposite h over 1. In other words, h equals tan theta. The height equals tan theta. Okay? So going over here, we have the height is tan theta. And so the area of the big red triangle is 1/2 times 1 times tan theta is just tan theta over 2. Okay? So that's the area of the big red triangle. Now let's look at maybe at the middle, actually let's do the other triangle since we're on triangles. Let's do the smaller blue triangle. Okay? So the smaller blue triangle. So let's get rid of all of this business. Let's actually get, no, let's leave that. Okay. So the smaller blue triangle is not right. Okay. It's not right. But notice what the base is. The base is still 1. The base of that triangle is still 1. That's nice. Okay, so let's do area, small, blue triangle. Sorry, I forgot the blue part. Now I'm going to put the triangle like that since that's not a right triangle. Equals, okay, of course, it's 1/2 base times height. That's how you find the area of a triangle. But we know the base is 1, so that's nice. So let's just go ahead and replace that with a 1. Now, how do you find the height? Now, this is not a right triangle. It's a scalene triangle. That means all the sides are different. But what is the height? The height can be found by finding what's called the altitude. The altitude is this point that is a perpendicular line to the base. So it's a line perpendicular to the base and it's passing through that other point. Now that does create a right triangle. Now it's not the overall right triangle, but we can use right triangle trigonometry to find that height here. This is h. That's the height of that triangle. So what could we say? All right. Oh, by the way, that 1 doesn't make a difference anymore. Sorry. Oh, no, that does. Yeah, it does 1. Sorry. That 1 is there. So we already had that 1, but I'm going to erase it because I don't want you to confuse you with the next step. Because with this next step, we need to relate theta, the height of the triangle, and not the base because we're only considering this right triangle right now, and 1 is not the base of that right triangle. But what do we know? This point right here is on the unit circle. So that's a radius. So it has a unit of 1. So I know the hypotenuse of this right triangle, and I want to know the, I guess that's the opposite side, and theta. So what trig function relates theta, the opposite side, and the hypotenuse? Was that sine? We could say that sine theta equals opposite over hypotenuse, so h over 1. In other words, h equals, h over 1 is just h, so h equals sine theta. So times sine theta. So we have 1/2 times 1, 1/2 times sine theta, that's just sine theta over 2. So that's the area of the blue triangle. All right. Now what about the sector? The sector is the green portion. Okay, like it's like a 2D ice cream cone. Okay, so how do you find the area of a sector? Hopefully I remember how to do this. So we're going to say area of green sector. Okay, and again, that's like the ice cream cone shaped. Here, let's do this. Let's see if I can draw a picture. Ice cream cone shaped, kind of like that. It's a sector of a circle. Now, okay, there's a formula from trig. Now, if you had trig recently, you might remember this. It is r squared, so the radius squared times theta over 2. Hopefully. We'll see if this works out in a few minutes. R squared theta over 2. Now, what's r squared? Well, the radius of this is it's a unit circle, so the radius is 1. So r squared is just 1 squared theta over 2, so you just get theta over 2. Again, r squared, r is 1, so r squared is 1. R squared theta over 2 just reduces to theta over 2. Now, we can write our inequality. This is the part of the squeeze theorem that we really need. This is the hard part to get usually. It's the inequality that says, hey, you have to have a middle function that's trapped between two functions on the left and right. And here's what we can say. The small blue triangle has an area of sine theta over 2. That's less than or equal to the area of the sector, which has a calculation area of theta over 2, which is less than or equal to the area of the big red triangle, which was tan theta over 2. Now, I'm sure you're wondering at this point, like, what the heck does that inequality have to do with that limit? Because it doesn't look at all like what we need right now. Okay, but bear with me. I think we can transform this inequality to get sine theta over theta in the middle. Just bear with me for a few steps. First of all, notice that everything is divided by 2. So let's multiply every portion of this inequality by 2. Remember, if you multiply by a non-negative number, you don't have to worry about the signs of the inequality. So let's just multiply everything by 2. And 2 being non-negative, so by 2, that's going to clear those denominators, which is nice. And that gives us sine theta less than equal to theta less than equal to tan theta. Okay, a little better, but still not what we need. We need sine theta over theta in the middle. So what if we maybe inverted this? Now, if you invert an inequality, like if you take the reciprocals of all the terms, that's fine as long as you reverse the inequality signs. In other words, I could write this as 1 over sine theta, as 1 over theta, and as 1 over tan theta. I can do that as long as I reverse the inequality signs. And do you see where I'm going with this? Now I have 1 over theta. What if I multiply everything by sine? Now in the middle I'll have sine theta over theta. And why can I do that? Well, guess what? If we're only letting theta be in the first quadrant, what do we know about sine? Sine has to be non-negative. So if I multiply everything by sine, I don't have to worry about reversing the inequality signs because sine is non-negative in the first and second quadrants. So if I multiply everything by sine theta by sine theta by sine theta, well, what do we get? We get sine theta over sine theta, 1 over here, less than equal to. In the middle, I have my now sine theta over theta, which is what I was after. And over here, I have sine theta times 1 over tan theta. Okay, so I gotta think about that. I have sine theta. Let's reduce this. What's tan theta? Tan theta is sine theta over cosine theta. But now I have a compound fraction. So I have sine theta divided by sine over cosine. If I take the reciprocal and multiply, I get 1, then I get sine theta over theta greater than equal to, I get sine theta times cosine theta over sine theta, and we get that. Okay, almost there. 1 greater than equal to sine theta over theta greater than equal to cosine theta. So now I have my inequality. That's the hard part for using the squeeze theorem. Now notice it is written backwards. Usually I like to write the inequalities from left to right instead of how it's written now. So let's write this. And again, this is the exact same thing. It just looks a little better in my book. Cosine theta less than equal to sine theta over theta less than equal to 1. That's the same thing. It just looks a little better. Okay, so that is the hard part. Now, if I can just show that the limit of the left and right functions as x goes to 0 is the same value, well, then I know that the limit of the middle function as theta goes to 0 is that same value. So let's be intentional here with what we write. We can say this. Since cosine theta is less than equal to sine theta over theta is less than equal to 1. And, okay, let's do our two limits. The limit of the left-hand function, oh, not as x, it's theta this time, as theta goes to 0 of the left-hand function, cosine, theta. Now what's cosine theta? Cosine theta, what's the domain? The domain of cosine is all real numbers. So we had a theorem that said basically for trigonometric functions along with other functions, if the function is defined at and I guess the word we'll need to use eventually is continuous at the value of c, then you can use direct substitution. So we can just simply plug in 0, cosine 0. What's cosine 0? Cosine 0 is 1. Okay? Now what is the limit of the right-hand function? The limit is theta goes to 0 of 1. Okay, that's a constant function. So what's the limit of a constant function regardless of the value of c? It's also 1. So since we know this inequality is true, and the limit of the left-hand function as x approaches 1, as x approaches 0, is equal to the limit as you approach 0 of the right-hand function, then the squeeze theorem implies that the limit as theta goes to 0 of sine theta over theta is equal to what? It's equal to that same value, 1. Because the limit of that left and right hand function on either side was 1, therefore the limit in the middle has to also be 1. Okay, let's look at the graph and see if the graph confirms our solution. Again, I don't expect you to know what this graph looks like. Sine x, I expect you to know what sine looks like, but not sine x over x, or sine theta over theta. Let's see here. Okay. So here's sine x over x. We're only concerned about the behavior as we approach 0, and clearly as we approach 0, we're homing in on 1. Now notice that at 0, the function is undefined. The function is undefined because you can't plug a 0. 0 is not in the domain of that function. So there is a hole there, but clearly from the right, the function, the y values are getting close to 1. From the left, the y values are also getting close to 1. So the limit indeed exists, and the limit as x approaches 0 of sine x over x, or as we wrote it, the limit as theta approaches 0 of sine theta over theta, that limit is indeed 1. Now, you want to memorize that and add that to your limit toolbox, because we will use that a whole lot in this class, at least for the next week, a couple weeks. We'll use that in the rest of this chapter. Whenever we're using we're solving trig limits. This will pop up a lot of times. Also, we'll use it in the next chapter when we're doing something called differentiation with trig functions. Okay? Alrighty, that wraps up this video. By the way, I don't necessarily expect you to reproduce this. I expect you to be able to follow along. Like, I would never ask you to reproduce all this on a test, for instance. But I would expect you to understand, okay, this is how we're using the squeeze theorem, and understand that what we've done is we've met the requirements of the squeeze theorem, by getting this inequality and then showing these two things are true, which satisfy the conditions of the squeeze theorem, which gave us our result over here. Okay, so I expect you to be able to use that result and understand and follow along. But I know this is a little, we had to review trig here and stuff. So I hope you should be able to follow along just fine. But as far as reproducing this test, I wouldn't ask you to reproduce this on the test. Okay. Usually if on a squeeze theorem type question on the test, it would be more along the lines of, say, the first example, where I just want you to make sure that you know how the squeeze theorem works, where maybe I give you the first condition, which is the inequality, and then you have to show Well, the limit of the right-hand function and the left-hand function as x approaches c is equal, which implies that the limit of the middle function as x approaches c is equal to that same limit. Okay? So that's the squeeze theorem. Again, the squeeze theorem in the wild doesn't happen very often, but when it comes in handy, it sure comes in and saves the day. And then just make sure to memorize this guy right here, because we will use that a lot in the near future. We're going to have it's called a special limit. We're going to have several special limits that you want to memorize and keep in your limit calculus toolbox for future use. All right, we'll show how to use this limit and show how it's so useful in the next video. I'll catch you there.